Hello. Today I want to talk about finding the shear graph and values in a really simple manner. I want to caveat this for any students who might be watching. You do need to abide by whatever is being asked for you if this is a coursework or an exam. So if you're asked to provide the functions for the shear force, that is the mathematical equation, you probably need to look at the other tutorials we've done. But if you just need the shear graph in a quick and dirty manner, this is the tutorial for you. So we'll discuss it, I'll show you 6 examples, and by the time we finish, you'll be ready to tackle shear for any beam that might be thrown your way. Now, before we begin, I'm assuming that you already know how to solve reactions. I'm not going to delve into them, I'm just going to assume you know them, and we're just going to start straight off from the reactions. The other thing I want to do is just go over this little diagram that I've drawn here. As you can see in this diagram, the shape of the shear force depends on the external loads of the beam. So if we have a point load like this, our shear force is going to be a constant, a straight line, like steps. If we have a UDL, our shear force is going to be a linear line, right? So a straight line between values, linear. And if we have something of a higher function, like a triangular load, then we're going to get a parabolic shear force. So the minute you know the rank of your load, you know the rank of the shear force. It's always +1. All right, I think we're ready. Let's get to it. Let's start off with this beam here with 2 concentrated loads, 120 kilonewtons and 60 kilonewtons. We've already solved this, so if you want to see a detailed discussion into the reactions, go to the previous tutorial. But I'm assuming that you understood that, and we're now looking at this beam here with the reactions already solved. Now, I'm just going to emphasize that I'm going to be using directions that suit the sign convention that we discussed earlier, and that sign convention says that this is the positive direction for axial force, this is the positive direction for shear force, and this is the positive direction for moment. And this is how we do it. It's really simple. We go up in the direction of the first force we have. I'm going to start from A. So in this case, I'm going to go up 100 kilonewtons. And as we said, we only have concentrated loads, so this is just going to be a constant. So I'm just going to continue that until something happens. We see at B, there's a force of 120, and that is going down, so that is in the opposite direction. So I need to go down 120. This is 120 in total. Just a reminder, I went up 100, got a straight line, went down 120, so that means if this bit is 100, I've reached -20. And once again, I continue in a straight line until I reach any new force or reaction. And here I see that I need to go down another 60. So I'm going to go down another 60. And if I go down another 60, I reach -80. And then I'm going to continue until I reach the last force, which, as you can see, makes me end at 0 because it is 80, but in the plus direction. Now we can see here that the jump here from the top of the 100 to the -20 is a total of 120, and that has to equal exactly this force here, right? And here you can see that I've got a jump from -20 to -80 of 60, which equates to that. So you can see every jump, this first 100, this second 120, this 60, and this 80, they are all graphed here. Now, according to my sign convention, this will work out as plus, minus, and minus. But if you're not sure about that, you can do a little check with this sign convention. And that's all there is to it. So hopefully that was really clear and straightforward. Let's see what happens in a similar beam, but this time a cantilever beam. So again, just looking at point loads. Okay, so this time we've got a cantilever beam. We solved this in one of the previous tutorials, and we got the reaction forces at the fixed end. So we're not going to look at the reaction forces, but straight into the shear force. So let's see what happens here. I go up 20, okay, so up 20, and then it's a straight line until I hit something new, which is this 20 going the other way. So here I've just had 20, and this is plus in my sign convention, and that's it. We've solved it without equations. So we've seen that graphing shear force diagrams for any point loads is really simple. You go up and you go down according to the direction of the shear load. But let's see what happens when you have a UDL. Now we need to remember when we have a UDL, the rank is one higher. So in this case, we're going to get linear lines. Let's have a look. So here I've got a simply supported beam with a UDL of 12 kilonewtons per meters along the whole beam. I've already solved the reactions and they work out as 54 kilonewtons at each end. So once again, I need to start off by going up. Initially, I just have that 54, right? So I go up 54 kilonewtons. And now I see that what is happening is that every meter I am going to go down 12 kilonewtons. I can calculate this, or I can also figure out where I'm going to end. Now I see that I need to end by going back up to 54, so I know that the end is going to look like this. And in between them, I just have the UDL, so it's just going to be a straight line going between them. Now, if I'm not sure about this, or I want to further validate what I'm doing, I might just do a cut, okay? So I would say I've got my reaction force, right, of 54 going up here. I've got my UDL coming down, and I've got my shear force drawn in the positive direction here. And if I were to do that, I would say that 54 minus 12 times 9, because I'm going to the end of the beam, and minus S equals 0. So S, the shear, is going to equal 54 minus 12 times 9, and that is minus 54 kilonewtons, which would give me this value here. So either way, if you do a quick calculation, or if you just have a look at this beam, you'll figure out that it is a linear line going from 54 at the top, or positive 54, to a negative 54. Let's now look at another UDL, but this time on a cantilever beam. So once again, I've already solved the reactions, and I've got 20 going up, so I'm going to start at 20. Now, to be honest, in this case, it's a cantilever. I know I'm going to end on 0, right? Because here, at this point here, there is no point load to give me a jump. So I know it's going to have to end on 0 at that free end. So I can just note that that is 0 and draw a straight line. Now, once again, if I do want to just check myself and figure out what that would be, I can just draw a little quick cut just to see what happens at the very end. What is S here? And I know that I've got a reaction force of 20 here, and I've got that UDL coming down of 5 kilonewtons per meters. And I just want to see what happens at the end. I want to double check. So I've got plus 20 minus 5 times 4, and minus S equals 0. So S equals 20 minus 5 times 4, which is 20, and that equals 0. If I just want to check the values at certain points, it's a good idea just to do the quick calculation and then draw the straight line between them. And for our last example, let's look at something when I've got point loads and UDLs mixed together. Alright, in this case, we're going to use this example that we've also solved. Here I have two reaction forces, an axial reaction force of 9 and a shear force of 17.68 at point A. I've then got this diagonal load I've divided into its components here. I've then got a UDL, and I've got this last reaction force at D. So really similar to what we did before. We're going to start at A. Make note that anything in the axial direction isn't in the shear direction, so it's not going to influence. So here I'm going to go up by 17.68. I'm just going to continue, right? It's not a UDL. I just continue straight line until I hit this next point of interest, right? Just here, where I have the 15.58. And that means that I need to now go down 15.58. So I'm going to reach 2.1. And I'm going to continue with that 2.1 until I reach the UDL. And then at the UDL, I now have a linear line. Now, once again, I know that I'm going to have to end on this, 21.9. I know that it's going to be a linear line between this point, and I can just draw it in. Positive, positive, and negative according to my sign convention. Now, once again, if I do want to check, I can choose to check at any point along that UDL and find out the same thing. But this is how to do it very quickly with no calculations. And that's it. That's how you find the shear force diagram for different kinds of loads, quick and easy, with the least calculations that you need to do. Now, again, that caveat, please do pay attention to what you're being asked. If you do have to provide the way that you found the graphs. If you do have to provide the formulas and the mathematical equations, obviously this method is not going to be enough. However, if you need to find the shear force diagram for all kinds of other methods that we'll discuss later on, then this is perfect. In the next session, I'll go over how to do pretty much the same for the bending moment diagram. Join me then. In the meanwhile, bye for now.